All right, here's today's do now. Given the piecewise defined function f of x is x squared when x is less than or equal to 3, or 2x plus 3 when x is greater than 3, determine if the limit of f of x as x approaches 3 exists. Pause the video and give it a try. All right, let's take a look. In order to prove that this limit exists, the limit has to be the same from the left and the right. So we have the limit as x approaches 3 from the left of f of x. We know from the left we are playing with this piece of the piecewise function. That is the limit of x squared as x approaches 3 from the left. Or in this case, 3 squared, which is 9. Otherwise, we have the limit of f of x as x approaches 3 from the right, which is the limit of 2x plus 3 as x approaches 3 from the right, because this is the piece we're now playing with, and that is 2 times 3 plus 3, which is 6 plus 3, or 9. So we're going to then say, yes, since the limit of f of x as x approaches 3 from the left is equal to the limit of f of x as x approaches 3 from the right, we know then that the limit of f of x as x approaches 3 exists and is 9. Consider the function f of x is equal to x squared minus 1 over x squared plus 1 as x increases without bound. That is, as x gets really, really big. Now, note, we can determine this by creating a table of values that get larger and larger. So remember, if typing this into your graphing calculator, you would want to type this in on your y sub 1, and then note you would want to type it in as x squared minus 1 in parentheses divided by x squared plus 1. Because if you do not group it properly, note that it will miscalculate. Now, taking a look at a pre-created table, approaching a really large number from the, or towards the right. So as x gets really big, we see that f of x, well, doesn't get really big. It gets stuck, right? It approaches a single value. Specifically, in this case, as x gets really large, f of x approaches the limit of 1. Now let's check on the other side. So going towards really big negative, as x gets really big negative, f of x, once again, approaches 1. So we have a couple of statements to make here. The first is the limit of our function as x approaches infinity, that's this first table, is 1. And then our second statement, the limit of our function as x approaches negative infinity is 1. When you look at the graph, it makes sense, right? We go forever to the right or forever to the left, and we're getting trapped by this horizontal line at 1. In this case, that means we have a horizontal asymptote, hence the title of our notes today. All right, let's give a definition. So let f be a function defined on the interval a to infinity, then the limit of f of x as x approaches infinity is L, means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. Basically, if we make x really big, then the f of x gets close to some singular value, L. And it works in the opposite direction as well. All right, the line y equals L is called a horizontal asymptote on the graph of y equals f of x if either the limit of f of x as x approaches infinity is L or the limit of f of x as x approaches negative infinity is L. Example 1. Use the graph of the function shown to draw reasonable conclusions for the infinite limits, limits at infinity, and the equations for any horizontal or vertical asymptotes. Here's a graph of the function. All right, let's start by drawing in what appeared to be our asymptotes. I'm going to use the highlighter, and let's use orange for our horizontal asymptotes. It looks like we have a line here, It looks like we have one here. And then it looks like we have a vertical asymptote here and one here. Okay, now let's go ahead and write some statements for those. Let's start with our horizontal asymptotes. So the limit as x approaches infinity of f of x. That is, if we go forever big, what value is our function getting closer to? In this case, 4. Okay, then we have the limit of f of x as x approaches negative infinity. And that is following our graph this way, and it looks like it's getting trapped by 2. Now, when both of these happen, this one tells us we have a horizontal asymptote at y equals 4, and this one tells us we have a horizontal asymptote at y equals 2. Right? In both cases. All right, now let's look at our vertical asymptotes. Okay, so we have one at 2. Now in this case, we have the limit of f of x as x approaches 2 from the left. Now from the left, it goes down to negative infinity. And we have the limit of f of x as x approaches 2 from the right. And in that case, it goes to positive infinity. Now that does mean that the limit itself doesn't exist, but it does also mean here that we have a vertical asymptote at x equals 2. And then let's check out our last one. We have the limit of f of x as x approaches, it looks like negative 1 from the left. We're going to infinity. And the limit of f of x as x approaches negative 1 from the right also goes to infinity. And therefore, we have a vertical asymptote at x equals negative 1. Now do note here, it is not necessary for those vertical asymptotes to approach that infinity in the same direction. All right, let's continue. Example 2. Find the limit of 1 over x as x approaches infinity. Okay, so let's look at the graph. This is our graph. And we are approaching infinity, so we're going this way. We're getting bigger and bigger. And it looks like we are getting trapped by 0. So logically speaking, this makes sense. Because if I have a singular object, say a sheet of paper, and I divide it an infinite number of times, it eventually goes towards 0, though that paper will never cease to exist, right? But it will get so small that it basically doesn't exist. Okay, now the exact same thing will occur going the other direction, right? So if we approach negative infinity, we have our 1 over x. If we follow it, it's going to get stuck again and go towards 0. Okay? All right, so we have this theorem based off of that idea. If r is positive and is a rational number, then the limit of 1 over x to the r as x approaches infinity will always be 0. Okay? Same thing in the other direction. Now this is important because we can use this idea to tackle some more problems. So we'd like to find each limit. Let's start with this one here. Now looking at this directly, it doesn't look exactly like this. So what our goal is here is to turn this problem into this idea. So what I'm going to do mathematically is I'm going to divide every single term by the same value or the same expression. So what we do here is we divide everything by the largest degree term. So I have here 3x squared over x squared minus x over x squared minus 2 over x squared. And then I have 5x squared over x squared plus 4x over x squared plus 1 over x squared. Now, mathematically, this is acceptable because I've done the same thing to the numerator and the denominator. So essentially what I'm doing here is I'm multiplying this entire expression by a 1. Okay, now this will then turn into the limit as x approaches infinity of 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. Now that we've rewritten this expression in a way that allows it to look like this theorem, we know that each of these individual terms, right, the ones that have some constant over, right, x to the r will go to 0. So we see here that goes to 0, this goes to 0, the 4 over x goes to 0, and the 1 over x squared goes to 0. That means then that the limit here is 3/5, meaning that we have a horizontal asymptote at y equals 3/5. Now looking at the graph here, if we follow this curve really, really far, really, really big towards the right, we do in fact see that it is getting stuck at 3/5, right? That 0.6. Obviously, we'd have to go much, much larger to truly see, but you see here, it is getting closer to 0.6 as we move along this curve. Now, if we follow the same idea and we approached it from the other side, which we're not actually going to right now, but if we did, you would notice in the graph that it also has a horizontal asymptote in the other direction at that same value. All right, this is what it looks like graphically. All right, let's try another one. Okay, so same idea, right? Our objective is to turn it into a form that is usable by that theorem. So we're going to divide by our largest degree of the two numerator and denominator expressions. In this case, that is x cubed. So I'm going to put every single term over x cubed. And then this is going to become the limit as x approaches infinity of 3 over x plus 5 over x squared and over 1 plus 1. Oh, sorry, I missed a term. Let's try to fix that. So 1 over x cubed. 1 over x cubed. Okay, now once again, every term that is some value, constant, over some x to some power will go to 0. So 0, 0, 0. So then we get here 0 over 1, which is 0. So that means then we have a horizontal asymptote at y equals 0. And this is what this one looks like.